Hey, it's Tim the tutor here, and in this video I am bringing you another topic in organic chemistry. This time we are tackling resonance, and I'm going to go over why your textbooks and your professors make this way too complicated, and I'm going to give you the easiest way to go about thinking about resonance. Let's first start off with the definition of resonance. And I'm going to give you a definition that you've probably never heard before because I haven't come across anybody else teaching it this way. Resonance represents the ability of electrons to freely move among adjacent p orbitals. If there are no p orbitals, there can be no resonance. So that means that electrons that are found in unhybridized p orbitals are free to flow into adjacent p orbitals and only into adjacent p orbitals. This also implies that electrons that are found in hybridized orbitals, such as sp3 orbitals, they are locked in place, and therefore they never have resonance. So, how can you tell if you can draw resonance structures for a molecule? All you need to do is look for two or more p orbitals on adjacent atoms. And literally, that is it. Okay, I guess I should probably go over the one exception to this rule, and that is the alkene. However, this is actually more a matter of historical precedent than how alkenes behave chemically. If you were to analyze reactions of alkenes, resonance actually can help you understand their reactivity. However, if you get a test question asking whether alkenes have resonance, you should definitely put no, because your professor is definitely going to take off if you say it does. Now the important part becomes being able to identify p orbitals. So how can you tell if an atom on a molecule has a p orbital? Well, first, atoms that are sp3 hybridized do not have p orbitals. That's because all three of the p orbitals have already been used to form the hybrid orbitals, so no p orbitals remain. Atoms that are sp2 or sp hybridized do have available p orbitals. In other words, if you see a double bond on an atom, or if you see a carbocation or a radical, you are looking at an atom that has a p orbital. Now here's the tricky one. Normally, an atom with a full octet, with the octet made of single bonds and at least one lone pair, is considered to be sp3 hybridized. In other words, it has no p orbitals. However, if the atom with the lone pairs is adjacent to another atom that does have a p orbital, then one of those lone pairs on that original atom is actually in a p orbital as well. This one takes a little bit of practice to get used to, so let's practice. What we're going to do here is circle all the atoms on these molecules that have a p orbital. Being able to identify atoms with p orbitals is a crucial skill, especially because for resonance, we need to have at least two p orbitals adjacent to each other, with the exception of just a lone alkene. As we said, by definition, historically, an alkene by itself is not going to have resonance. So let's take a look at this first structure. In the top left, there are no atoms on there that are not sp3 hybridized. So all of those are sp3 hybridized, so there's no p orbital. In the second one, we do have a carbocation. That means we are electron deficient, and that molecule has a central atom that is sp2 hybridized, which means there is an empty p orbital. So that central carbon there has a p orbital. Likewise, this third molecule has a radical. If you haven't covered radicals yet, radicals do not affect hybridization. So in other words, you can treat a radical like you treat a carbocation. In other words, that central carbon there is sp2 hybridized, with the radical itself being found in a p orbital. The last one in the top row has a negative charge, which implies that there's a lone pair on that central carbon. A lone pair by itself is usually found in a hybrid orbital. It requires that there's an adjacent p orbital to it in order for it to be found in a p orbital. So in this last one, we do not have a p orbital, and that central carbon is sp3 hybridized. In the second row, we have a bunch of molecules with double bonds. And as was mentioned previously, if there is a double bond on an atom, it has a p orbital. That's a pi bond, and pi bonds are made of p orbitals. So in this first alkene, there's a p orbital on both of the carbons involved with the double bond. For the second atom, not only do we have those same two carbons, but we also have a carbocation, and again, a carbocation is a sign of a p orbital, an empty one. Likewise, as in the first row, a radical also indicates that we have a p orbital, so we have these three p orbitals as well. And for the last one on the right, we have the same p orbitals associated with the double bond, but also now we get to apply that tricky rule. If you have an atom with lone pairs and it's adjacent to a p orbital, then that lone pair itself is in the p orbital. In other words, that carbon with the lone pairs must be sp2 hybridized because its lone pair is found in the p orbital because it's adjacent to an atom with a p orbital. For the first molecule in the third row, we're looking at a carbon-oxygen double bond. And anytime there's a double bond, both atoms involved in the double bond must have a p orbital because the electrons in a double bond are found in adjacent p orbitals. The second molecule, if you look at it, the only thing that we have are lone pairs on the oxygen, and lone pairs themselves are not enough for you to identify a p orbital. In fact, that oxygen has two lone pairs and two sigma bonds, and it's not adjacent to any p orbitals. That carbon next to it is sp3 hybridized because of that hydrogen that is invisible in the skeletal structure. So in other words, all of the atoms on this second molecule are sp3 hybridized, so there's not a p orbital. In the third molecule, we do have a carbocation, so that indicates we have an empty p orbital on this carbon. The oxygen has lone pairs, and because it is next to an atom with a p orbital, then one of those lone pairs is in the p orbital itself. That means that this oxygen also has a p orbital. And the final molecule here, we have the OH2 on the end. So we have that positively charged water-leaving group. And notice that that is not a carbocation. That is just a formal charge that is actually on the oxygen, or it's on that OH2 leaving group. So, in other words, we have one lone pair on that oxygen only. It has three sigma bonds and one lone pair. And because it's not adjacent to a p orbital, again, there's not actually a carbocation next to it, then that has to be sp3 hybridized. So that last molecule on the right has no p orbitals. In this last row, our focus is going to be on the halogens, in this case fluorine, and the halogens, when they're single bonded, have three lone pairs. So in the first molecule in the last row, we just have lone pairs by themselves on the fluorine, and they're not adjacent to any p orbital, so there are no p orbitals on that molecule. Everything's sp3 hybridized. For the second one, however, we do have a carbocation, which indicates that we have a p orbital on this carbon. And again, because there are lone pairs on the fluorine, we actually have one of those lone pairs in a p orbital as well. So that means the fluorine is sp2 hybridized, and one of those lone pairs is in a p orbital. For the third molecule, we actually have a benzene ring, and we have the fluorine attached to the benzene ring. And every place where we have a double bond, there is a p orbital. So all 6 of these carbons are double bonded, so there's a p orbital on all of them. And because the fluorine has 3 lone pairs, one of those lone pairs is going to be in a p orbital since the fluorine is adjacent to an atom with a p orbital. So every single atom on this molecule has a p orbital. And then the very last structure on the right, that carbocation is not adjacent to the fluorine. So there is a p orbital over here. However, that is too far away. It is 2 atoms away from the fluorine lone pairs. So the lone pairs on the fluorine are not adjacent to a p orbital. Therefore, none of the lone pairs are in the p orbital. So there's only the one p orbital at that carbocation position in that last molecule. Now that you know how to identify p orbitals, the next step, of course, is being able to draw resonance structures. So the first step is identifying all the atoms in a molecule that have a p orbital. And then again, we're looking for 2 adjacent atoms with p orbitals, with the exception of a carbon-carbon double bond by itself. So if you have that, you can draw resonance structures. So then we're going to draw arrows to move electrons among those atoms with adjacent p orbitals. And an arrow always begins at a region of electron density. So in other words, at a radical, a pi bond, or a lone pair. And it always ends at an atom or a bond. Please never draw an arrow from a carbocation to something. A carbocation means an absence of electrons or an absence of a bond. And when we draw arrows, we're showing movement of electrons. And a carbocation literally means nothing's there, and you can't move nothing. Now, an arrow with a single head indicates the movement of a single electron, and you should only be using these if radicals are involved. Normally, we use an arrow with that double head, which indicates you're moving a pair of electrons. Now, the net charge on all resonance structures must be the same, so make sure you indicate positive and negative formal charges every time you draw a new resonance structure. And then you can just continue drawing resonance structures over and over again until you have moved the electrons through all of the adjacent p orbitals. What we're going to do next is we're going to go through some common examples. And if you don't get good at these basics, you'll be in trouble. So make sure you get really good at these. In this first example, we have two double bonds that are adjacent to each other with a single bond in between. If we analyze the p orbitals, you'll notice that all four of those carbons are sp2 hybridized, so all of them have a p orbital. So we can move those electrons anywhere we want in this region. So the first thing I'm going to do is I am going to draw an arrow from this pi bond right to this middle bond, and that's going to create a double bond in the middle and get rid of the double bond on the right-hand side. However, carbons can't have more than 4 bonds, so that means we need to push these other electrons to the end, otherwise we violate the octet rule. Remember, there is a hydrogen here, so that would give us 5 bonds on that carbon if I didn't get rid of that other double bond. When I do that, I get my first resonance structure for this conjugated diene, and that gives me a double bond in the middle, and it shows that I have a lone pair and a negative charge on the left side, and a carbocation on the right side. Of course, I could have gone the other direction as well, so if I wanted to show a different resonance structure, I could have moved the electrons the opposite direction. And this, of course, would have given me a resonance structure with the lone pair and the negative charge on the right and the carbocation on the left. So in total, we have 3 resonance structures for this molecule. In the second molecule, we have 3 overlapping p orbitals. We have the sp2 hybridized carbon that has the carbocation, and then we have the 2 involved in the double bond. So again, we can only move electrons from regions of high electron density. So that means we're going to start at this pi bond, and we're going to draw the arrow from this region of high electron density to this region of low electron density, moving a double bond to this position. What that's going to do is going to give us a resonance structure that looks like this. In the third structure, we have a radical, which is a single unpaired electron, and this is adjacent to a double bond. So again, we have 3 p orbitals that are next to each other. However, a radical is only a single electron, so we have to use this single-headed, or I guess the half-headed arrow, as it's sometimes called. And that's going to move a single electron. Now, the pi bond here has 2 electrons in it, but we only need 1 of them. So we're going to have this also, we're going to have this half-headed arrow. It's going to go join up with this other half-headed arrow, and that's what's going to form a new double bond in that spot for the new resonance structure. But we still have 1 electron left over in that pi bond, so this has to go on the end. So we have 3 half-headed arrows, and when we draw the resonance structure, what does that make? It essentially creates a double bond in this position, and now we have a radical on the end. In our final example on this page, we do have a lone pair adjacent to a p orbital. That means that the lone pair itself is going to be in a p orbital. So again, we have 3 p orbitals that are adjacent to each other. And here we have the highest region of electron density at that lone pair. So what we're going to do is we're going to draw our full arrow to this position, and that is going to force the electrons here to go to the end. And of course, that will give me a resonance structure that looks like this. Now let's go a little beyond just those four basic structures. In the structure on the left here, we do have two p orbitals that are adjacent to each other, but one of the atoms is more electronegative than the other one. That allows us to draw this resonance structure right here. Notice that the original charge on the first resonance structure was 0, and in the second resonance structure, we have put a negative charge on the oxygen, and we put a positive charge on the carbon. That makes it still 0. So this is a valid resonance structure. For the second molecule here, we do have lone pairs adjacent to a carbocation. Therefore, we can do a resonance because we have one of the lone pairs in a p orbital. So this one is fairly straightforward. We draw an arrow from one of those lone pairs, and we're going to create a double bond right here. This third molecule is very similar in what we can do with resonance as the second molecule. However, the third molecule is something that is important to recognize as it comes up in carbonyl chemistry a lot in Orgo 2. But the idea is the same. We have lone pairs adjacent to a p orbital, so that means one of the lone pairs is in the p orbital, and we can draw a resonance structure by drawing this arrow right to that position, giving us this final structure here. The last molecule here is the acetate ion, which is the conjugate base of acetic acid. Being able to draw resonance for this molecule is very important, especially when you're trying to understand how acidic something is or how basic something is. So the resonance structure here involves being able to recognize that we have a double bond. So again, there's a p orbital on each of the atoms in the double bond, and we have lone pairs adjacent to the carbon in the double bond. That means one of those lone pairs, of course, is in the double bond. So we can draw a resonance structure that moves these electrons on the oxygen to the bond between the carbon and oxygen. And of course, that's going to break the octet rule, and we can't do that, so we need to now break this double bond and move these electrons as well. That, of course, will give us this final resonance structure right here. On this page, we'll draw some additional resonance structures for some molecules that are a little more complicated than the basics we've gone over on the last two pages. So for this benzene ring, notice that all 6 carbons are sp2 hybridized and have p orbitals. What that allows us to do is draw resonance structures where the electrons move around the entire ring simultaneously. So every time we move one, it displaces another bond, because again, we can't have 5 bonds on any carbons. So that gives us a resonance structure that simply makes it look as though those bonds have shifted positions. With the next structure, once again, every single carbon in the molecule is sp2 hybridized, which means we have p orbitals on every single carbon. So we can draw multiple different resonance structures to show the movement of the electrons. So we're going to start at one of the double bonds, and we are going to draw an arrow towards this bond here. That's essentially going to move that carbocation to a different location. That's going to give us another structure. That looks like this. And of course, we have a carbocation next to a different double bond, so now we can draw another resonance structure. And of course, if we can do that, we can do it again. And finally, we can draw one more. And that is all the resonance structures for this second molecule. On the last molecule, I do want to point out a couple of things. First, we do have one carbon that is sp3 hybridized. That's the one in the top left. So that one cannot participate in resonance. Second, the nitrogen on the right is adjacent to a p orbital. So the lone pair on that nitrogen is also in a p orbital, which makes it sp2 hybridized. That allows it to participate in resonance. The nitrogen in the bottom left, although it has a lone pair on it, that lone pair itself is not in a p orbital. That's because there's already a double bond on the nitrogen, so the p orbital is already occupied because of that double bond. So the lone pair on the nitrogen in the bottom left cannot participate in resonance because it's not in a p orbital. With that being said, let's go ahead and draw the resonance structures by showing how the arrow pushing works. Notice here that in the first resonance structure, it was neutral. There was not a separation of charges. When I drew the resonance structure by moving that lone pair, I pushed the electrons onto that carbon on the bottom right there. That actually caused a charge separation in that second resonance structure, or the first one that I drew, putting a positive formal charge on the nitrogen and a negative formal charge on that carbon. Overall, the molecule is still neutral in this resonance structure, so that is allowed. For another resonance structure, we're going to move this lone pair over here, and that's going to force this one in the other direction. I can continue drawing resonance structures by simply moving this lone pair around the ring. Finally, I have one more that I can draw. Now I'm going to draw in that lone pair on that bottom left nitrogen to show that it did not in fact move and was not involved in drawing any of these resonance structures. Now that we know how to draw resonance structures, being able to determine the major contributor to the resonance hybrid is important. That's because not all resonance structures are weighted equally. Here are some of the rules for determining which structures best represent the actual molecule. This is not an exhaustive list, but will apply to most scenarios in introductory organic chemistry. The first rule, the most major contributor will have the greatest number of complete octets. The resonance structure on the left has all carbons with a complete octet. The one on the right has a carbon that is a carbocation. Therefore, it only has 6 valence electrons, so the more major structure is the one on the left. The most major contributor will have the fewest number of formal charges. You can see the molecule on the left has no charge separation at all, whereas its resonance structure on the right has 2 formal charges. So the major contributor, again, is on the left. If a structure must have a negative charge, the more major contributor will have the negative charges on the most electronegative atom. In this case, oxygen is way more electronegative than carbon, so it makes more sense to put the negative charge on the oxygen. That makes the one on the left the more major contributor to the resonance hybrid. The most major contributor will have the greatest number of covalent bonds. That includes both single and double bonds. Notice the molecule on the left has 4 covalent bonds, whereas the one on the right only has 3. You may also notice that this is also supported by the first rule: the most major contributor will have the greatest number of complete octets. Sometimes the rules overlap and reinforce each other. So again, the one on the left is more major. Last, if a structure has an aromatic resonance contributor, it will be the major contributor. You may recognize benzene at this point in your organic chemistry career. Benzene is an aromatic compound, which you'll learn a lot more about in the future. The resonance structure on the right breaks up that benzene ring and puts the positive charge in a place of where that double bond was. So the aromatic resonance structure on the left is a more major contributor. Now, sometimes rules will conflict with each other. In those cases, usually the structure that violates the least number of rules will be the major structure. And if you have 2 resonance structures that are equivalent or roughly equivalent, they both can be considered major. If you got something out of this lecture, please feel free to like this video and subscribe to this channel. If you have any questions or comments, leave a message below. And last but not least, if you want more help or want easy access to valuable organic chemistry resources for free, be sure to check out the notes underneath this video with a link to join our community.